Okay, 2019 free response question number 6. This is a non-calculator question. They've given you 3 functions introduced right here. All of them are twice differentiable, which becomes really important in this problem. And they gave you the value here of g of 2 and h of 2, both equaling 4. They've given you the equation of a line that's tangent to both g at x equals 2 and h at x equals 2 as well. And that's all the information we were given, so let's get rolling. First question right here, we're supposed to find h prime of 2. So remember that for any curve that we have right here, if we want to find the value of its derivative at a particular spot, we are really just looking for the slope of its tangent line. And they gave us right up here the equation of that red tangent line at this particular spot. So what we're looking at right here for h prime of 2 is that h prime of 2 is simply equal to the slope of its tangent. And as we look at this equation here, which is given to us in something similar to point slope form called point slope equation, that 2/3 right there is the slope of that tangent. And that is how we get our answer here for part A of 2/3 for that slope. So that was A. Not a whole lot of points probably allocated to that one. All right, as we take a look at part B right here, it says to let A be a function given by this convoluted mess right here, 3x cubed multiplied by the function h of x, and 2 questions here. First, write an expression for A prime of x, and then use that expression to find the value of A prime of 2. So, A prime of x first. If we're going to take the derivative of A of x, what we need to notice is that this is actually 2 different functions here being multiplied together, 3x cubed times h of x, so that's going to require the product rule. First times derivative of the second plus second times derivative of the first. So A prime of x would be, first factor is 3x cubed, derivative of the second is just going to be h prime of x, plus the second factor, which is h of x, times the derivative of the first, which is going to get us a 9x squared. So I've underlined that because that's the answer to the first question, right? An expression for A prime of x, and you just want to make sure that you've labeled that clearly. Now to the second part, they want us to find the value of A prime of 2. So we're going to take that expression we just came up with right here and plug a 2 in everywhere there was an x. And some of that is straightforward, like the 3 times 2 cubed and the 9 times 2 squared right here. But when we plug the 2 into the function itself of h prime of 2 and h of 2, we've got to use some information that they gave us earlier in the problem. So here we go. The 3 times 2 cubed is going to get us a 24. The h prime of 2 is exactly what we were asked to find here in part A. And all of a sudden now we realize why it was that they wanted us to use that or find that. So that 2/3 comes right down here. Multiplied by here, or excuse me, added to the 9 times the 2 squared is going to get us a 36. And h of 2 was given to us in the original problem right here where they tell us that h of 2 is equal to 4. So we went ahead and put a 4 in right there. The 2/3 times the 24, remember guys, mentally this is 24 divided by 3, which is 8 times 2, and that's where that 16 comes from. The 36 times 4, remember guys, if you're bemoaning not having a calculator here, multiplying by 4 is easy. You just double the number and then double it again. 36 doubled is 72, 72 doubled is a 144, and the 16 and the 144 gets us 160 for the value then of A prime of 2. So zipping right along, that takes us through part B, and let's see what's going on with part C right now. So this is where it gets interesting. They've given us a new function, a definition of h of x, that's defined in terms of f of x. So it's x squared minus 4 over 1 minus f of x cubed for all x values not equal to 2. Now this is an interesting piece of info they've given us. It is known that the limit as x approaches 2 of this function h of x can be evaluated using L'Hopital's rule. They've included the s right there. And remember guys, when we talked about L'Hopital's rule, that there's only a few circumstances where that applies, but typically L'Hopital's rule applies when you try to do direct substitution for your limit and you end up with either 0 over 0, which happens a lot, or infinity over infinity, which happens a little bit less often. But one of those things has to be the case right here in order to do that. So as we take a look at what I wrote down here for part C, I actually did this a little prematurely. This was not something I probably should have done yet, and I realized it as soon as I applied L'Hopital's rule and did the derivative of the top and the derivative of the bottom. I ended up with this mess right here, but realized that we didn't know these values, so that got me thinking I kind of made a wrong turn right there. So let's kind of start over here for part C, right about here, and see what's going on here. Now, when we look back at the numerator of h of x, the x squared minus 4, it's pretty easy to see that the limit as x approaches 2 of that numerator is going to equal 0. That tells us that it's this format right here, which is the reason why L'Hopital's rule applies to this problem. So, since the limit as x approaches 2 of the numerator has to equal 0, or does equal 0, we can conclude then that the denominator's limit has to be 0 as well. So the limit as x approaches 2 of the denominator, 1 minus f of x cubed, has to equal 0 also. So with that in mind here, the only way that we can get this expression right here to equal 0 is if f of x right here, or we should say the limit as x approaches 2 of f of x, that would have to equal 1 as well. And since we know that f is differentiable, we know that we can simply take the 2 and plug it in right there and get that limit. So that tells us right there, everybody, that the value of f of 2 has to equal 1. That was one of the things they wanted. The other thing they wanted in part C was the value of f prime of 2. So to figure that one out, this is where I needed to actually take my L'Hopital's expression that I started early right up here on the top. Oops, sorry, you can't see that one there. That this expression right here where we applied L'Hopital's. So let's take a look here. I got the 2x by taking the derivative of the numerator, which was the x squared minus 4. The denominator here, the 1 minus f of x cubed, we took the derivative there. The derivative of 1, a constant, was 0. The derivative of this expression was the negative 1 times the 3, so negative 3, times the same base to the exponent, f of x squared, and don't forget the chain rule now, times the derivative within of f prime of x. So that is where this whole denominator came from right above. Okay, so now back to this expression right over here. We were trying to actually evaluate this limit right here by plugging a 2 in everywhere that we had it right up here. Okay, so what happened here? The x on the top became a 2, the 2x's on the bottom both became 2's as well, and this is where we were at. Now, the fact that we knew that h of x was a differentiable, twice differentiable function meant that it was continuous at that spot as well. And that meant that the limit as x approaches 2 of h of x just had to be equal to the value of h of 2 itself. Remember, everybody, that the definition of a continuous function is one whose value, h of 2, is equal to the limit as x approaches 2 of that same function. And we knew already from the givens in the problem that h of 2 was equal to 4. So long story short, this whole expression right here, the limit as x approach 2 of h of x, has to eventually equal 4. So trying to clean that up just a little bit underneath right here. Let's see what's going on. We now have a 4 up on the top. Down on the bottom, the value of f of 2, we knew that, from right here, that f of 2 was equal to 1. So the negative 3 times 1 squared was just going to get us a negative 3, times the f prime of 2, which is still unknown, but we knew all of that had to equal 4. So I multiplied this denominator over here to the right and got negative 3 times 4 to make a negative 12. F prime of 2 was equal to the previous numerator of 4. Divided both sides by negative 12 and got this answer that f prime of 2 was equal to a negative 1/3. That was a pretty tricky problem. Okay, and then from there, let's move on to part D. And in part D, they tell us now that we know a hierarchy right here, that g of x has to be less than or equal to h of x for everywhere in between 1 and 3. And there's a new function, k, that is stuck right in between the g of x and h of x. So what do we have? A lower limiting function here of g of x and an upper limiting function of h of x. That made me think about the sandwich theorem right away, that k of x is sandwiched in between. And if you remember this back when we did these types of limits in chapter 2, I think, what would happen is that you would have one function up here on the top, and in this case, sorry everybody, you'd have one function up here on the top, and in this case that'd be h of x, another function down on the bottom, and that's going to be g of x, but the only way this works is if those two functions kind of come together and hit at one particular moment right here, and that is going to be g of x. Well, the reason we know that works is because they tell us right over here that g of 2 and h of 2 are both equal to 4. So back to our little graph right over here, that basically tells us that this ordered pair right here, when x was 2, both of those functions took on a y value of 4. And now we know that k of x is less than or equal to h of x and greater than or equal to g of x on that entire interval. So what very often happened back in chapter 2 is that our middle function would just kind of be something that would be oscillating back and forth, but it would have to pass through that same point in the middle here in order for k of x to satisfy this given bit of information right over here. So what that shows us right here is that k of x has to pass through that same point right there of 2, 4. So let's take a look at how we actually justified that for our answer here. So for part D, here's what we knew. We knew here that the limit as x approaches 2 of g of x had to be equal to g of 2. Again, we knew this because it told us that g was differentiable, which means it was also continuous, and that's why that limit had to equal 4. By the same rationale, the limit as x approaches 2 of h of x, because h is also differentiable and therefore continuous, had to equal h of 2 as well, which was 4 also. So that limit was 4, this limit was 4. By the squeeze theorem, that now told us that the limit as x approaches 2 of k of x had to equal 4 as well. Now that piece of information might seem like what you needed right there, but remember, just saying right here that a function has a particular limit doesn't guarantee that the function is continuous. With what we know so far, k of x might have had a hole right there at the 0.24. But going on, they gave us this information here also. G of x was less than or equal to k of x, which was less than or equal to h of x for all values of x in between 1 and 3. So since g of 2 was equal to 4 and h of 2 was equal to 4, we could conclude that k of 2 had to equal 4 as well. So what's going on? We've got a limit as x approaches 2 of k of x equaling 4, and we know that the value of k of 2 itself was equal to 4 as well. And since all that plays out, we know then that the value of k of 2 is equal to the limit as x approaches 2 of k of x, and that tells us then that k is continuous at that value of x equals 2.